Welcome to today's paper reading. Today's paper is titled, Self-Taught Evaluators. This paper was published on the AR14 preprint by Tianlu Wang and colleagues from Metafair. In this work, the authors address the critical role of model-based evaluation in the development of successful models. This evaluation serves as a reward model during training and can replace human evaluation. However, the standard method of training such evaluators involves collecting a large number of human preference judgments over model responses, which is both costly and results in data that quickly becomes outdated as models improve. To overcome these challenges, the authors propose an innovative approach that improves evaluators without the need for human annotations, relying solely on synthetic training data. Their method involves an iterative self-improvement scheme that generates contrasting model outputs and trains a large language model, LLM, to act as a judge, producing reasoning traces and final judgments. This process is repeated at each new iteration using the improved predictions. Remarkably, without any labeled preference data, their self-taught evaluator can enhance the performance of a strong LLM, Llama 3-70B Instruct, from 75.4 to 88.3 on reward bench, outperforming commonly used LLM judges like GPT-4 and matching the performance of top-performing reward models trained with labeled examples. Large language models, LLMs, heavily depend on strong evaluators throughout their development lifecycle. These evaluators are used during training to align with human preferences and for iterative self-improvement, and during inference as an alternative to human evaluation. Enhancing evaluation capabilities benefits the entire workflow, including the scientific research process aimed at developing better techniques. However, building strong evaluator models typically requires large amounts of high-quality preference data from human annotation, which is costly and time-consuming. This dependency on human-generated data poses challenges for scaling to new tasks and maintaining relevance as models improve. In this work, we explore an iterative self-training approach that uses no human annotated preferences, relying purely on synthetically generated data. This method involves generating contrasting synthetic preference pairs and using the model as an LLM-as-a-Judge to generate reasoning traces and judgments, which are then used to train a superior LLM-as-a-Judge. This approach has shown significant improvements in accuracy on benchmark tests. In the realm of evaluation, large language models, LLMs, have been proposed as effective evaluators. These models can function as classifiers that directly output scores, or they can use a prompting technique known as LLM-as-a-Judge, which generates a chain of thought explanation to justify judgments. Additionally, responses can be scored individually or compared in pairs. On the other hand, synthetic data has proven to be a valuable resource for acquiring training examples, especially in scenarios where real-world data is difficult to obtain or annotate. This data can be tailored to meet specific evaluation criteria or safety constraints. Synthetic data has been instrumental in model alignment, enhancing model capabilities, and teaching new skills. In the context of evaluation, synthetic data has been used to assess tasks such as factuality, safety, coding, and general instruction following, often showing strong correlations with human judgments. Techniques like the Weston approach have been employed to improve reward models by creating preference pairs from model outputs. For LLM-as-a-Judge models, synthetic responses have been generated to prompt the LLM to produce responses of a specified quality. Figure 1 illustrates the iterative training scheme of the self-taught evaluator. The process begins with a seed model that generates contrasting synthetic preference pairs for a given input. These pairs are then evaluated by the model acting as an LLM-as-a-Judge, which produces reasoning traces and judgments. The labeled data from this evaluation is used to train a superior LLM-as-a-Judge, which then iterates the process to further self-improve. This method eliminates the need for human annotated preference data, relying solely on synthetically generated training data. The method involves using a large language model as a judge, LLM-as-a-Judge, to evaluate user instructions and assistant responses. The model takes an input instruction X and two possible responses Y, A, and Y, B, and outputs a preference for which response is better. The training process is iterative, starting with a large set of user instructions and categorizing them using the LLM. For each instruction, a pair of synthetic responses is constructed, one of higher quality than the other. In the judgment annotation phase, the current model samples up to n times to generate reasoning traces and judgments, filtering out incorrect ones to construct the training set for the next iteration. The training process begins with an initial model, M0, derived from Llama 3-70B instruct. This model undergoes iterative fine-tuning using the FAIRSEC2 library, with the negative log likelihood loss applied exclusively to the evaluation portion of the training data. The selection of instructions and responses involves a large pool of human-written instructions from the WildChat dataset, which are categorized using the Mixtral 22BX8 instruct model. Synthetic responses are then generated based on these categorized instructions. The evaluation of the self-taught evaluator model is conducted across several benchmarks, including Reward Bench, MT Bench, and Help Steer 2, each with specific protocols to measure the model's accuracy and agreement with human judgments. In the Reward Bench evaluation, the self-taught evaluator achieved an overall score of 88.3 on iteration 5, significantly outperforming the seed model's 75.4. With majority voting, the performance further improved to 88.7. On MT Bench, the self-taught evaluator showed an agreement score of 79.5, comparable to GPT-4-0125's 79.1 and better than the seed model's 77.8. For Help Steer 2, the self-taught evaluator improved both average accuracy to 71.6 and position-consistent accuracy to 71.0, compared to the seed model's 65.2. Table 1 presents the results of our self-taught evaluator on the Reward Bench. The model, trained on synthetic data without human annotated preference labels, shows significant improvement from an initial score of 75.4 to 88.3 by iteration 5. Employing majority voting with 32 samples further enhances performance to 88.7, surpassing many existing reward models. This demonstrates that our approach can match, if not exceed, the performance of top-performing models trained with labeled data. Table 2 presents the results of our self-taught evaluator model on the MT Bench dataset. The model, trained solely on synthetic data without human annotated preference labels, demonstrates performance comparable to GPT-4 judgments. Key metrics include 0 to 1 accuracy and position-consistent accuracy, highlighting the model's ability to match human-like decision-making in complex scenarios. Table 3 presents the results from the Help Steer 2 validation set, demonstrating that iterative training on synthetic preferences enhances position-consistent accuracy when compared to the Llama 3-70B instruct model. The evaluation is conducted on the Help Steer 2 validation split, highlighting the improvements achieved through this training method. Table 4 illustrates the impact of supervised fine-tuning with synthetic preferences sourced from various categories on the performance of Llama 3-70B instruct. The results, measured on Reward Bench, show significant improvements across different categories, with the largest enhancements highlighted in bold. This demonstrates the effectiveness of incorporating diverse synthetic data sources to enhance the model's performance in multiple skill areas. In this section, we explore the effectiveness of different synthetic data sources for training a strong LLM-as-a-Judge. We found that data sources focusing on various skills, such as coding and mathematical reasoning, are all effective. These sources generally improve the categories in Reward Bench that are related to their distribution. We also experimented with generating synthetic bad responses by creating similar instructions and then generating a good response for these, which serves as a bad response for the original instruction. This approach, using a specific prompt template, achieved a Reward Bench score of 80.7. Additionally, we examined the impact of combining synthetic preference data with human-labeled preference data. This combination showed improvements in model performance, retaining strong performance across different data mixing weights. Figure 3 illustrates the distribution of the curated training set of selected instructions in comparison to the full WildChat dataset. The dataset exhibits a long-tailed distribution of input length, with the majority of examples containing less than 500 tokens. In contrast, the full dataset includes a cluster of very long instructions, often comprising long-form coding instructions or transcripts. Figure 4 illustrates the distribution of inferred complexities for the curated training data compared to all instructions present in the WildChat dataset. The complexity is inferred using a score ranging from 1 to 5, with 1 indicating the lowest complexity and 5 the highest. This figure helps in understanding the complexity distribution across different subsets of the dataset, providing insights into the difficulty levels of the instructions used for training. Figure 5 illustrates the distribution of estimated output lengths between the curated training data and all instructions in the WildChat dataset. The curated dataset shows a tendency towards shorter output lengths, reflecting a more focused and concise set of instructions. In contrast, the full dataset exhibits a broader range, with a notable cluster of longer output lengths. This difference suggests that the full dataset includes more complex and detailed instructions, possibly due to the presence of long-form coding instructions or transcripts, which are less common in the curated subset. This analysis highlights the varying complexity and detail levels between the two datasets, which could influence the training and performance of models utilizing these datasets. Figure 6 illustrates the distribution of inferred categories between the curated training data and all instructions in WildChat. The curated dataset predominantly contains complex instructions related to logical reasoning and science. In contrast, the full dataset shows a higher proportion of instructions focused on relationships and entertainment. This categorization was inferred using the Llama 3-70B instruct model, which assigns a complexity score and category to each input instruction. Table 6 illustrates how combining different data sources in varying proportions can enhance the performance of a fine-tuned model. The synthetic preference data used in this study was generated with the Llama 3-70B instruct model. The proposed approach demonstrates superior performance, achieving a score of 83.8, which outperforms other methods. In this study, the authors present a scalable approach to construct a strong generalist evaluator for LLM outputs. This method relies on synthetic preferences generated without human annotation. Through iterative training on these synthetic preferences, the self-taught evaluator significantly enhances the accuracy of a strong seed LLM, specifically Llama 3-70B instruct, from 75.4 to 88.7 on the reward bench metric, setting a new state-of-the-art for generative LLM-as-a-Judge methods. However, the limitations of this approach are not detailed in the provided text, indicating that further research is necessary to identify and address potential areas for improvement. The generative LLM-as-a-Judge models used in this study have several limitations. Firstly, these models typically produce longer outputs, which results in higher inference costs compared to simpler reward models that output a single score. Specifically, the models used in this work are 70 billion parameter models, which are computationally expensive. Secondly, the approach relies on a capable seed model to generate synthetic preferences during the iterative training process. This assumes that the model can produce reasonable evaluations, and there has been no investigation into whether smaller models could achieve similar results. Lastly, the study focused solely on pairwise evaluations, comparing two responses, and did not explore the possibility of using these models to score individual responses. Evaluating single responses is left for future research. In this section, the authors acknowledge several key contributors who have supported the project. Jing Su and Janice Lan provided essential discussions and overall support. Ken Baliago offered feedback and support in training large language models using the FAIRSEC2 library. Nathan Lambert assisted with the reward bench tool. Additionally, Yutian Deng and Yejin Choi provided help with the WildChat platform. Thank you for watching.